Hi, I'm going to talk about inclined planes. And inclined planes are just ramps, basically. Okay? That's all they mean. It's a really standard type of AP problem, is the inclined plane problem. And so what you want to be able to do is know how to do this just as fast as you can possibly do it, because they're going to throw so many curveballs at you at different times that understanding the basic problem makes it so much easier to understand all the other things. So I'm going to talk about a mass M with some friction sliding down the ramp, okay? So it's going to slide down the ramp. We could have an inclined plane problem where it's sliding up the ramp. I give it a bump and it's sliding up and it's going to slow down. We could have a pulley up here, and we could have things, being pulled on each other. That's a multiple body problem. That's also on an inclined plane. So you can see you really want to know how to do the inclined plane problem for more complex situations. Okay, so mass M, and it's sliding down, and the angle of the ramp is theta. Now, if the ramp is really flat, there's not going to be much force pushing it down the ramp, and I'm going to talk about where that comes from. If it's really tilted, that force down the ramp is going to be almost like mg, almost like the force of gravity. Let's look at the forces that are acting on that, okay? So when we do a free body diagram, or when we try to evaluate forces, we look at field forces, and there is only the one, which is gravity, which is straight down, okay? And that acts on the center of mass, mg, which is not so important in this problem. I'm going to get a darker color, okay? So here's mg, the force of gravity down, that's acting on the center of mass. And then we go around it and we say everything else has to be a contact force. So the contact, there is only the one contact, and it's a surface, and surfaces commonly have two forces. One would be the normal force, which is perpendicular, pushing up, and it would be pushing right like this up from the surface. That's the normal force. And the force of friction. If we're sliding up, friction would be down the ramp. Sliding down, friction is up the ramp. So friction would be acting at the surface in this direction. Okay? So what I've done is really a force diagram here. I've shown where all the things are acting. That becomes important if you have a ball or something like that. But this isn't rotating at all. It's sliding. So, and when we get to rotation, we'll talk about how those different forces look together. So we can just draw this. We're just going to draw this on a free body diagram. Again, we represent it with a square or a circle. And we say the force of gravity, which I just write as mg, m times g, the normal force. And you're starting to see why we don't always assume normal force equal to mg. It's just not true most of the time. And the force of friction. Okay. Something is really interesting about this. Remember, when we talk about this, we do a free body diagram, then we break it into components in a frame of reference. So there's my free body diagram, FBD, but frame of reference is a little different this time. Instead of this, we know it's not going to accelerate this way or that way. We can make the problem quite a bit easier by tilting our frame of reference. What I mean by that is what we're going to do is we're going to say down the ramp, parallel to the ramp in other words, is going to be one dimension, and perpendicular to the ramp is going to be another dimension. I'm going to call this positive, I'm going to call this positive. Okay, I'll consider that to be my x and my y up that way, but that's my frame of reference now. It's nice to be, it's handy to be able to create your axes, your orthogonal or perpendicular axes, so the acceleration that's going to happen is going to only be in one of those dimensions. And so what we've done here is, look, all of a sudden this normal force, I don't have to break that down anymore. Force of friction, I don't have to break that down anymore. mg, I do have to break down. And that's a little tricky, okay? If we look at the dimensions of this, and let me write the components. The components would look like I'd have something going down here and something going down here. Let me draw them up here. Okay, if this is the coordinate axes, if these are the coordinate axes, this here, if you can see it, would be the component of mg in that direction. You got to really just tilt your head to see that this is what it is. If you just tilt your head here, you can see how far is that going down, how far is that going to the right. Okay, that's a little tricky, but we can use the fact that that is theta. That means if this is mg, this is going to be actually 90 minus theta. So this would be the sine of 90 minus theta times mg. This would be the cosine of 90 minus theta. But the cosine of 90 minus theta just ends up being the sine of theta. Okay, I'm not going to go through all the trig and all the complementary angles and all that. I don't want you to have to either. I want you to memorize this. The part of the force that's pointing down the ramp is called mg sine theta. Okay, the part that's pointing into the ramp is mg cosine of theta. And I'm going to draw it over here. So mg sine theta and mg cosine theta. We knew it was going to break down that way somehow, but I'm telling you that the sine one goes down the ramp. Friend, former physics teacher at the school I teach at, she and a friend were hiking up a hill, and their legs were getting tired, and the friend said to her, damn mg sine theta, meaning I'm fighting mg sine theta as I walk up the hill. Mg sine theta is how much of my gravitational force is pulling me in the opposite direction. Okay, so mg sine theta, damn mg sine theta is down the hill. Mg cosine theta is into the hill. If we had a meter stick, which I really should have thought to bring, if I push something on this, you'll see the meter stick bends like this, and that force pushing out on the object that you put on the meter stick, that's the force, the normal force that is basically induced by the fact that you are pushing into the ramp. Okay. A way to think of this mg sine theta, sine is small for small angles. Small for small angles. Okay, so if you have a really small angle, not very much force is going to put you down the ramp. Okay, most of that weight is pushing down into the ramp at a small angle. At a really big angle, almost all of that mg is pushing you down the ramp. Okay? So, when I do that now, I've got my free body diagram. Now I want to do my frame of reference. Keep it angled. Keep it so it kind of looks like that. Now, I've got normal force. Let me use a different color. I've got the normal force in the same direction it was. I've got friction in the same direction it was. But now I've decomposed this. I've said, okay, mg sine theta is the part of that down the ramp. Sine theta, damn mg sine theta, the one we fight when we're climbing. And mg cosine theta is how much of the force of gravity is pushing into the ramp. Now, this ends up taking us in the same direction we always have. We've gotten these two. Once you've got these two, you're in great shape because now you're just writing two Newton's second law equations. Okay? Again, I'm going to call this the x direction. I'm going to call this the y direction. So in the x direction, sum of forces in the x direction equals ma in the x direction. Okay? And then I'll just put it over here. Sum of forces in the y direction equals ma in the y direction. Okay, well this is mg sine theta in the positive direction. Remember I called that positive. Mg sine theta minus the force of friction. Force of friction is pushing in the negative direction in this case, if it's sliding down, equals ma in the x direction. Okay? The y direction, that's all I can really do right now. Eventually, when we've learned friction and we know how to calculate friction, friction is related to the normal force. So I'm going to show you what we do with that in a second. So in the y direction, we've got an interesting thing. We've got the normal force pushing out, and we've got mg cosine pushing in, pushing down in the negative direction, equals m times the acceleration in this direction. This block is not going to fly off the ramp. The block is not going to plunge into the ramp. This acceleration is 0. So what we found is the normal force will be equal to mg cosine theta. And this happens an awful lot of the time. Fn equals mg cosine theta. That's a big deal, okay? If there are no other forces in this direction, if nobody's pushing on that or pulling on it, then normal force is going to be equal to mg cosine theta. That happens most of the time. We can use that normal force, and again, I'm jumping ahead if we haven't done friction yet, but friction, there's an expression called mu times mu times the normal force. So we could substitute this in and have mg sine theta minus mu times the normal force, which is mg cosine theta, equals ma in the x direction. And you'll notice masses cancel out, and the acceleration is g times sine theta minus cosine theta. That's just doing the math. If you can set up that equation and that equation, you are in fantastic shape on the inclined plane problems. The rest is just math, which I say all the time, but it's true. And then you're going to be substituting some things in. So what do you need to be able to do? You want to be able to draw that free body diagram. Check. Not a hard thing. We can do free body diagrams. You want to be able to break this into components, knowing that mg sine theta is down the ramp, mg cosine theta is into the ramp. Then you want to be able to take that and write 2 Newton's second law equations. Free body diagram, frame of reference, 2 Newton's second law equations. And if you can do that, the rest is just math.